Greetings everyone, my name is Andrei Esipov and I'm a program manager on OneDrive and SharePoint team. And I'm here along with my co-host Aninda, who is an engineering manager on OneDrive and SharePoint team as well.
Hey everyone, I'm Aninda Ray. I'm a principal engineering manager in the OneDrive and SharePoint experiences team.
We're extremely excited for you to be joining us today for a behind-the-scenes look at how we at OneDrive and SharePoint architect our web applications for scale and performance, how we approach web performance in general, and how do we design for it. We'll also take an early look at some of the cool new tech that will power performant OneDrive and SharePoint experiences in the very near future. We can't wait to share all of this with you, and we're hoping that you can apply some of what you learned today to your own web apps. We will primarily focus on the following three topics today. First, we'll look at how do we approach web performance in OneDrive and SharePoint. Next, we'll have a discussion around best practices for how to architect your web applications for performance. And finally, we'll discuss the latest tech that we're building to power amazing and modern web app experiences in OneDrive and SharePoint in the very near future. Let's dive into the realm of web performance and how we approach it ourselves in OneDrive and SharePoint web applications. Web performance is more important than ever. We're living in a world where ubiquitous, everyday high-speed networking in an enterprise environment is not as available as before, and we're now getting accustomed to getting our work done on bandwidth-constrained home networks. And personally, this is how I experience the web every day now, through this laptop that's connected to my home wireless network that I'm sharing with my wife, who is also now working remotely full-time. And that is why performance is as critical as ever. We need to ensure that our users can continue to effectively use our web applications and have a delightful experience when doing so, regardless what network that they're on. For the rest of the session, we'll do a deep dive on several approaches and techniques that we employ in OneDrive and SharePoint web apps to ensure a great experience on all types of networks. And hopefully you'll be able to implement some of these techniques in your own web apps. We have a host of web applications in OneDrive and SharePoint. Some examples of them include the SharePoint Online Portal, SharePoint Framework, OneDrive, and Microsoft Lists, just to name a few. Our primary goals when it comes to web performance revolve around making web apps more delightful to use and load as quickly as possible on first as well as subsequent visits. We need to ensure that how we design our web apps allows us to scale to millions of active monthly users across the globe, while delivering consistently great performance across various devices, device form factors, and networking environments. And finally, ensuring that our users get the absolutely optimum experience when using our web apps through modern browsers. Our current performance efforts are primarily focused on optimizing how our users experience our web apps through modern browsers, such as Microsoft Edge, Internet Explorer 11, and Edge Legacy are being retired in 2021. And we highly recommend you adopt modern browsers if you haven't already, to fully benefit from all the performance work that we're putting into our web applications that take advantage of the modern browsers APIs. Let's switch gears a little bit and talk about how we approach measuring web performance. Fundamentally, our aspiration is to load and render the most relevant content to our users as fast as possible and ensure that our users can interact with this content smoothly and efficiently. We can think of a page load process comprising of 4 various stages as perceived by the user of the web app. The first phase corresponds to the user perceiving if the page is actually loading. Next phase is whether the displayed page content is useful, followed by a phase where the user perceives the content to be usable, meaning that the user can actually interact with it. And finally, are those page interactions seamless and smooth? We specifically focus on optimizing how fast we can display useful content on the screen and how quickly we can make that content interactive. To measure those user moments, we primarily rely on 2 metrics across our web apps. First one is called First Meaningful Paint, or FMP for short, to measure load times of the useful content. The second metric that we're focusing on is called Time to Interactive, or TTI, to measure how long does it take for the content to become interactive on the page. Our main objectives revolve around minimizing the time to first meaningful paint and reducing or eliminating any delays in making that content interactive. When it comes to improving content load times, we optimize for rendering of primary content first, such as SharePoint home site content And only when the primary content has been rendered, we follow it by loading other page elements, such as navigation menus. Again, we're measuring primary content load times using first meaningful paint. When it comes to page interactivity, we're aiming to make web apps interactive as soon as possible by reducing or ideally eliminating any delay between the time the primary content is displayed on the screen and when that content becomes interactive. And we rely on time to interactive metric to help inform our work in this area. So what methods do we use to actually measure and record web performance? We use a combination of lab measurements and real user measurements. Lab measurements allow us to have a consistent and reproducible method for evaluating web performance across various builds, and usually serves as the first line of defense for any possible regressions. But ultimately, we rely on real user measurements as the source of truth for how the web apps perform in the wild, to ensure that our users across the globe are actually reaping the benefits of the work that we're putting into making our web apps faster. Specifically, we're focused on measuring and optimizing for the 75th percentile of our users, as it allows us to understand how the majority of our users experience the web apps on most common types of networks. Additionally, we're also focusing on addressing the 95th percentile, as it allows us to understand how users on slow networks or low-end devices experience our web apps. It's important to focus on both of these measurements to holistically understand how various types of users experience the web app. Now that you know how you can start approaching web performance measurements, Aninda, can you tell us a bit more about how we implement those measurements in our web applications?
Thanks, Andre. At the outset, I want to re-emphasize that performance matters. A performant web application is essential for productivity. It drives user engagement, increases retention, and improves adoption. The importance of performance is even more pronounced during these times, where many of us must work in non-ideal settings, including low bandwidth devices and unreliable network conditions. We at ODSP take performance seriously and hold ourselves accountable for delivering high-quality user experiences. While we measure progress against multiple internal metrics, success is measured through improvements we make against these two KPIs. So how do we quantitatively measure performance against these key metrics? Let's start with FMP. As illustrated here, a viewport is the visible area of a document on a display device. The goal here is to measure the time to render components in the viewport without penalizing performance through expensive DOM queries. We ship applications with static and dynamic layouts. Now, measuring the time to render viewport content for a static layout-based application, like your OneDrive for Business or the SharePoint Start page, are relatively straightforward, as these components nor the layout change very often. It gets a bit more challenging with dynamic layouts, like a modern site page with first and third-party web paths on a multi-column canvas. We leverage modern browser's Intersection Observer API to observe the intersection of components within the viewport and identify a subset that exceed a threshold. Time to measure these components to render is the FMP for that page. Next, let's take a look at TTI. JavaScript runs on the browser's main thread, alongside style calculations, layout operations, and paint. A browser is unable to respond to user actions when long-running tasks are in progress. To measure the time to interactivity, we need to identify the time for the main thread to acquiesce, as in not perform any long-running tasks so it can respond to user actions. We leverage modern browser's Performance Observer API to observe long-running tasks and identify an idle time window where there aren't any such tasks. The time to reach this idle state is then measured as TTI.
Thank you, Aninda. That is super interesting to understand how some of the key web performance metrics are actually measured. If one wants to improve on these performance metrics and meet the desired goal targets, what are some of the most important considerations to take into account?
Modern ODSP web applications are client-side rendered single-page applications. Server page handlers emit boilerplate HTML that allows browsers to load the pertinent JavaScript libraries required to generate application HTML. While there are multiple advantages to client-side rendering, one of the biggest challenges is to improve the time for initial page render. All ODSP applications must adhere to fundamentals, basic principles, if you may, to minimize this. These include establishing a performance budget. As we build richer experiences, the amount of collateral, including scripts and APIs, necessary to serve these increases, which adversely impacts performance. Every application must adhere to its performance budget, which sets limits on the size of static JavaScript and the number of APIs required to reach its KPIs. Features are measured against this budget, and anything that exceeds it needs to be re-evaluated, requiring optimizations or scope reduction. Improving content delivery. We need to quickly deliver static assets and data required to start applications. We do this in multiple ways, including reducing server latency to process the document request, including optimizing the HTTP request pipeline and the corresponding page handlers to serve the response. Serving static assets and images from CDNs as they're delivered faster due to better proximity to the user and reliance of optimized cache settings. Leveraging HTTP2, which uses efficient header compressions and improves network utilization by allowing multiple concurrent exchanges on the same connection. And finally, reducing the size of static application scripts by relying on Webpack to do code splitting and removing unused code. All application scripts are minified and compressed to reduce the transfer size of a network. We also leverage file name hashing to increase browser cache hits, since the hashes of stable file modules don't change very frequently. Optimizing the critical render path. This is the process where a browser takes HTML and CSS markup to generate the corresponding object models, combines them to build a render tree, computes layout to determine the position of each node in that tree, and finally paints. The faster this path, the more performant the experience. We optimize this by loading non-critical components either lazily or on demand. Some of our applications rely on route-based loading, where we load the primary view by default and subsequent routes are loaded on demand as the user navigates to them. We serve additional data as stream of HTTP responses, making them available to the application earlier, thereby minimizing the need for the application to issue these requests after boot. We progressively render our applications over multiple frames instead of blocking until the entire DOM is constructed. This enables a continuous render experience. Accelerating to interactivity. Time to interactivity is almost as important as the time to first meaningful paint. We improve interactivity by reducing operations that block the main thread. These include minimizing UI reflows, which is the process of recalculating the position of elements in the document and re-rendering it. We optimize reflows by reducing the number of DOM updates, managing the depth of the application DOM, and avoiding complex CSS selectors. These also help us minimize jank or shifts in layout. Eliminating long-running tasks which result in dropped frames and sluggish experiences. We emphasize a pay-for-play model where components are loaded on demand. These are some of the ways we ensure our out-of-box experiences adhere to these fundamentals to provide a fluid and performant experience.
These are some great tips, Aninda. When building custom SharePoint portals, can our third-party developers also take advantage of the work that the product team has been putting into web app fundamentals and performance?
Yes, absolutely. See, performance is bound by the slowest component in the viewport. Now, dynamic layout-based applications are particularly affected by this, where we cannot control the extensions or the customizers or the web parts that exist in the viewport. So we strive to provide the rails, expose the APIs, and communicate best practices via the SPFX framework, which enables our third-party developers to build components with the same basic principles. Similarly, we provide the tools and dashboards like Why Slow to our site owners so they can visualize the performance profile and understand its impact on the engagement and retention of users on their sites.
Aninda, once you reach your desired performance targets, how do you ensure that you're able to sustain those target performance numbers release after release?
That's a great question. Performance is a journey requiring diligent course correction. If left unchecked, it's quite easy to regress. So holding the line is really important. And here are some ways where we sustain our gains. Through instrumentation, we leverage browser's performance APIs to track navigation and resource timings, allowing us to measure the time to load a document and its resources. We inject custom markers that enable us to drill into the performance profile of an application's lifecycle. Further, we have invested in elaborate dashboards that allow us to visualize trends. Auditing. We have dev tools in place to audit every pull request submitted by ODSP engineers to evaluate its impact against the performance budget. We audit performance of every new build and block rollouts in case of regressions. We also run performance experiments on every new feature to minimize the scope of regressions. Further, we maintain active and passive monitors that track the performance of course scenarios, raising escalations on encountering regressions. We also conduct monthly status reports where ODSP applications are evaluated against progress made towards the stated KPI goals.
100% agree with you, Aninda. Achieving exceptional performance is definitely not a one-time effort, but rather an ongoing journey. We learned how executing against fundamentals allows for providing quality user experience. Aninda, beyond simple fundamentals, what are some of the recommendations that you have if one wants to truly see breakthroughs in performance of their web applications? How can modern browser APIs be leveraged to deliver a consistently performant experience, one that is resilient to network and service degradations?
To provide a continuously smooth experience, browsers need to process 60 frames per second, or 1 frame every 16.7 milliseconds. This includes the time to execute scripts, calculate styles, render layout, and paint. To ensure this frame rate, we must reduce the amount of work on the main thread so it can prioritize paint and response to user actions. We do it in some of the following ways. Handling navigations as in-place DOM updates instead of full-page loads. Updating only the content region is more efficient than repainting the whole document. Leveraging worker threads that allow us to move compute and IO-intensive tasks to dedicated web workers, or boot our applications by leveraging service workers. Relying on web storage APIs to serve precompiled static assets and data. And investing in a service aggregator capable of understanding query expressions and streaming information over a single connection. In-place navigation, worker threads, web storage, and optimized data aggregators serve as building blocks for the next generation ODSP web architecture. Following is an illustration of what that looks like. ODSP web experiences are highly interconnected, with deep links that take you to different applications. Navigating from the SharePoint start page to a modern communication site that shows up in your frequent feed. then clicking on a node in the site header to navigate to its corresponding page library are all common operations within a user session. Instead of triggering full-page reloads, we aim to provide a seamless experience as a user navigates through these scenarios. We do this through investments in a runtime that allows in-place navigations across single-page applications. Common layout and Chrome are persisted across application boundaries, and we only modify the content region through in-place DOM updates. This is more efficient than reloading the whole document. It significantly reduces compute cycles on the main thread, thus improving both the end-user perceived latency and the time to interactivity, while delivering a consistent experience. Further, a shared runtime allows reuse of resources and data, thus improving performance while reducing costs. Similarly, instead of having one service worker per application, which would trigger expensive service worker re-registrations as you navigate across them, we rely on a shared runtime composed of multiple controllers, each managing the boot sequence of their corresponding application. A single worker instance allows reuse of static resources, data, and information across applications, thereby improving the boot times holistically across ODSP experiences. We follow the same basic principle for web workers with an orchestrator worker model where each worker manages some aspect of computer I/O, say uploading telemetry, accessing local stores, running analytics and cleanup tasks, which no longer have to be served on the main thread. All these components rely on local web storage APIs, which enable them to function offline. Finally, applications still do need to make API requests to serve the latest information. Instead of issuing multiple concurrent requests, we are investing in solutions that allow clients to express data needs as GraphQL expressions. These are then served from a dedicated service aggregator endpoint that manages request orchestration across multiple service workloads and streams partial responses over a single connection. The next-gen web architecture makes our applications fast, reliable, fluid, and offline. Applications fulfilling these requirements are treated differently by web browsers, allowing them to be installed. Yes, we are transforming ODSP web applications into PWAs that bring the best of web and native. Going forward, ODSP experiences will be installable with one click. You will be able to launch a standalone list experience right from your home screen. Furthermore, as modern browsers keep enhancing its support for PWAs, you will be able to leverage them with one click.
Why don't we take a quick look at how you can experience a SharePoint portal as a progressive web app? Progressive web apps are easily installable through the browser and launch instantaneously. Browsing and interacting with the app is fast and smooth. If you want, you can pin the app to your start screen or taskbar for easy access. Progressive web apps offer excellent performance, and this particular SharePoint site with lots of media content loaded in just over 1 second. You can close and search and launch a PWA app just like any other application. And these are just a few of the benefits of progressive web apps. There's one more exciting thing that we would like to talk about today, specifically how we're planning on moving beyond progressive web apps to truly supercharge OneDrive and SharePoint web applications. While progressive web apps provide great capabilities such as local installation and native app-like behavior and offer some offline capabilities, we really need to think beyond progressive web apps in order to provide fast access to extremely large and complex data sets, as we often find in SharePoint. Accomplishing various tasks beyond simple content browsing, such as editing a large list stored in a SharePoint experience, needs to be fast, smooth, and reliable, even when network connection is subpar, or during periods of heavy use. Additionally, we need to be able to provide full web app experiences that involve complex editing tasks, even when offline, far beyond what even progressive web apps can offer today. We are excited to let you know about Project Nucleus, an exciting new technology that will power the next generation of OneDrive and SharePoint web applications. Project Nucleus will help deliver fast and smooth experiences and make web app data available to you regardless of the network state. It accomplishes this by establishing a durable cache of the web app data on your local device and by syncing the data with the web application using a standard set of APIs. As a result, you will be able to get powerful browsing and editing capabilities when you're not even connected to the network. Project Nucleus is built on an extensible framework that will allow different web applications to take advantage of its capabilities. Let's take an early look how Project Nucleus can enable blazingly fast and always-on experiences in one of OneDrive and SharePoint web applications, Microsoft Lists. Project Nucleus allows you to accomplish common tasks at blazing fast speeds, like column sorting and grouping, even on lists with hundreds of thousands of rows. List interactions are fast and fluid, making working with large lists a true delight regardless of your internet connection speed. And all the changes that you make online are then synced with the local durable cache. What's even more impressive is that Project Nucleus will enable you to work with your lists even when offline. Imagine being able to work on your list when you are in a train or airplane. You can accomplish the same tasks offline as you could when you are connected to the internet. You can add and remove list filters, change list views, sort and group columns, and even make offline edits. And all the changes that you make offline are uploaded and then synced when you are reconnected to the internet, allowing you to continue working where you left off. And this is just a sneak peek of the new exciting capabilities that will be powering some of our web app experiences in the very near future. We covered a lot of ground today, and we really hope that you found how we approach web performance on OneDrive and SharePoint insightful and learned something new that you can apply to your own web applications. In summary, remember that building performant web applications is absolutely vital to delivering delightful user experiences. Invest in performance measurements and focus on fundamentals to make strides towards fast and responsive web apps. When it comes to OneDrive and SharePoint web applications, use modern browsers to get the very best experience when it comes to performance, and make sure to stay tuned for how we will power the next generation of OneDrive and SharePoint experiences with progressive web apps, fast data access, and Project Nucleus. It was a true pleasure having you join us today, and if you want to learn more about how to build performant SharePoint portals, tune in to the following sessions. Again, thank you.